It is Kiran Musunuru who has done the most historic gene editing. It's made global news because it's precision gene editing of a 7-month-old baby suffering from a fatal disease. And Kiran Musunuru and his team created a personalized gene engineering which was delivered in vivo into this live baby. And the baby has not only survived but thrived. It is an absolute cutting-edge frontiers of medicine. It is personalized precision medicine.
Baby KJ Muldoon was born here at the hospital of the University of Pennsylvania. Everything seemed to be going smoothly, and then within a couple of days after he was born, he became devastatingly ill. He had very high levels of a toxic metabolite called ammonia in his blood, and that's very toxic to the brain. His only hope would be to get a liver transplant to replace the broken enzyme in his liver, just replace the whole liver, which obviously is not the best solution, but the only one available. And he wouldn't be able to get a liver transplant probably until he was at least a year old to do it safely. And so within a few days after he was born, got whole genome sequencing, which is a way we have now of determining the identities of all 3 billion letters in the human genome, in his case, his personal genome. And in looking through all the 3 billion letters, figuring out exactly what misspelling is causing his disease. And that gave us the answer. But that misspelling looked like it could be fixed or potentially fixed by a new technology we have called gene editing. The particular type of gene editing is known as CRISPR. And the beauty of this technology is that it can be very, very precise.
The next session, is something that I've personally been really waiting for and anticipating. It is Kiran Musunuru, who has done the most historic gene editing. It's made global news because it's precision gene editing of a 7-month-old baby suffering from a fatal disease, a liver condition, a kidney condition, which where protein is not processed properly, and it was life-threatening. And Kiran Musunuru and his team created a personalized gene engineering which was delivered in vivo into this live baby, and the baby has not only survived but thrived. It is an absolute cutting-edge frontiers of medicine. It is personalized precision medicine. We're going to show you a very tiny clip of the baby that is at the center of this drama. Unfortunately, Kiran has not been able to join us in person, but we did not want to let go of this session because it really is truly inspirational. It's in that realm of fundamental foundational science where there's no dilemma and dialogue around it. It's just pure inspiration. We're going to show you a little bit of that film and then go right into that session. We have Coperni after that, which is fashion and technology, and then a brief town hall with the robots. I thank all of you who've been so patient to be here on a Sunday afternoon. Hi, Kiran. Thank you so much for joining us virtually. I was just sharing with the audience that we did not want to let go of this session, even though you couldn't join us in person, because it's just so inspirational, the work that you've done. So just, in a nutshell, would you share with our audience what exactly was baby Muldoon suffering from, and what is the therapy that you and your team of doctors came up with?
Certainly. Well, thank you so much for having me, even though I couldn't be there in person, and hopefully the virtual feed is coming through clearly.
Yeah,
You
can
can hear me?
everyone hear him? Yes.
Okay, perfect. So KJ, baby KJ Muldoon, was born here at the hospital of the University of Pennsylvania. Everything seemed to be going smoothly, and then within a couple of days after he was born, he became devastatingly ill. Very, very sick. It wasn't entirely clear what was happening, but the physicians who were taking care of him sent off a bunch of laboratory tests and other types of testing and quickly came to the answer. He had very high levels of a toxic metabolite called ammonia in his blood, and this meant he had a certain type of disease called a urea cycle disorder. And there are about 6 or 7 or 8 different types of urea cycle disorders. These are very, very, very bad diseases. Basically, there is this ammonia that's a breakdown product of protein that you eat in the diet. We all make it. It's very, very toxic, but we have a series of enzymes in the liver that convert the toxic ammonia into something called urea, which is not toxic and can actually be passed out of the body very easily. And so all of us have no issue eating as much protein as we need or want. But in a kid with a urea cycle disorder, this ammonia can't get broken down, can't get metabolized properly. Any one of those 6 enzymes is broken. And so it built up to very high levels in his blood, this ammonia, and that's very toxic to the brain. And so that's what he was suffering from. He was taken across the street to the Children's Hospital of Philadelphia, to the intensive care unit. He got dialysis, cleaned the ammonia out of his blood, but only temporarily. It was very clear that he was going to be very, very sick. He never left the hospital. His ammonia levels were checked very, very frequently. Anytime he had a common cold or a stomach bug or a common childhood illness, the stress on his body would cause the ammonia levels to climb. And so there's real concern that he would take continued hits to the brain and it would decline over time. And his only hope would be to get a liver transplant to replace the broken enzyme in his liver, just replace the whole liver, which obviously is not the best solution, but the only one available. And he wouldn't be able to get a liver transplant probably until he was at least a year old to do it safely. And so that meant there was this whole year where he was just going to be exposed to this ammonia and decline over time and maybe not even survive until he got the transplant. What we decided to do was something different. And so within a few days after he was born, got whole genome sequencing, which is a way we have now of determining the identities of all 3 billion letters in the human genome, in his case, his personal genome. And in looking through all the 3 billion letters, figuring out exactly what misspelling is causing his disease. And that gave us the answer. He had a misspelling in a gene called CPS1, which makes one of the enzymes in that chain of enzymes that breaks down the ammonia. And because he had that broken enzyme, couldn't clear the ammonia. But that misspelling looked like it could be fixed or potentially fixed by a new technology we have called gene editing. The particular type of gene editing is known as CRISPR, which many of you I'm sure have heard of. And the beauty of this technology is that it can be very, very precise. If you put it into the cell, a human cell, and you take this CRISPR, it has 2 components. You have a protein that actually does the so-called editing. It can make a change in the DNA. You have a second component that's like a GPS. And so what you do is you can actually program in a sequence of about 20 letters into that GPS, and then those 2 components come together, the protein, the GPS, they form a little molecular machine, and it can scan the entire human genome, all 3 billion letters, and find just the one place that's specified by the GPS, whatever place in the genome matches the 20 letters you programmed in. And so what we were able to do is program the GPS so that it went to the location of KJ's misspelling in his gene, CPS1 gene, with the idea that it could potentially correct that misspelling and get the enzyme working again, turn it back on. And if we could get that to happen, then he would be able to handle the ammonia and break it down just like any of us do. It would be a lot healthier. Now, big challenges, well, there are several challenges, but the big challenge is how do you actually get this into the body? And so it turns out, just over the last few years, have been able to develop this technology where you can fabricate billions or even trillions of these little soap bubbles, tiny microscopic soap bubbles and actually put the CRISPR cargo within that soap bubble. And then infuse these soap bubbles, again, billions, trillions, into the bloodstream, just through intravenously, an infusion. And once it hits the bloodstream, it goes straight to the liver, which is where all this stuff is happening. It works well because the liver can clean things out of the blood, which is its purpose, to take things out of the blood. So these soap bubbles get taken up by all the cells in the liver. The CRISPR cargo is released. The GPS is already programmed to go to the site of his misspelling. It goes there, and then the idea is that it corrects the misspelling. And the hope was that we could get enough of the cells with the misspelling corrected that they would start making the enzyme and then be able to clear the ammonia. Now, the challenges were we've never seen his misspelling before. It's unique to him. Basically, no one else in the world has this misspelling, and so we couldn't know what misspelling he had before he was born and he became sick, and we actually sequenced him. So there wasn't any time to prepare beforehand. You couldn't have predicted and had the drug ready to go. So we had to start making it from scratch from when he was born. The second challenge is that he didn't have a lot of time, right? So he was already starting to, have these, what we call ammonia crises or metabolic crises, where he'd have a cold or stomach bug, and the ammonia levels would rise in the blood and put him in danger. And we needed to act as quickly as possible. We didn't even have a year, we thought. We needed to get it down to several months. And somehow, even though there was no precedent for trying to do this whatsoever, actually making a whole new drug from scratch, personalized to one kid from the time he was born, in 6 months we were able to actually get this treatment made specifically for him. It wouldn't do anything for anyone else in the world, but specifically for him to correct his misspelling. Got it made in 6 months. Got clearance from the regulatory authorities here in the United States. It's the Food and Drug Administration, the FDA. And before he was 7 months old, he got the treatment. And we weren't sure. Yeah, we weren't sure whether it was going to work. But within about a week, it became clear that his ammonia levels looked really good. We gave him more protein in his diet than he had ever been able to take in before. He got very little protein because it's toxic to him. And so before he got the treatment, he was at the 9th percentile body weight for his age.
Wow.
And then after the treatment, we found he could take in a lot more protein, actually a normal amount of protein for someone his age, which he had never been able to do before. And it was a great sign, and his ammonia levels stayed stable. And then since then, this is almost a year ago now, actually, the first anniversary of his treatment is 3 days from now, February 25th, 2025. So we're right up against the first anniversary. But since he got that treatment when he was a little less than 7 months old, his ammonia levels have been entirely normal, despite him taking in a full amount of protein. He went through this growth spurt. After about 2 to 3 months, 3 months in the hospital, he got a couple of follow-up treatments just to make sure it was working. He was doing so well, we realized there's absolutely no reason for him to be in the hospital anymore. And there was no talk anymore of having a liver transplant. So he went home with his family. He's been doing fantastically well ever since. He's indistinguishable from any other healthy child you can imagine. He's hitting all his milestones. The only thing that distinguishes him is perhaps he's the happiest baby you've ever met. He's just full of unbridled joy, insatiably curious, very, very friendly. I think being in the hospital for 9-10 months, he just got used to lots of strangers coming into his room and seeing him, and so he's just unfazed by anything. And so he's doing so well, and couldn't have asked for anything more. And it really, even though I'm a scientist and I think very rationally about things, everything has gone so well. It really does. I have to conclude that it was something of a miracle.
That's incredible, Kiran. Most miraculous story, So, Kiran, there's so many things that I'd love to ask you, but I just want to stay with baby KJ a little bit. One is that, for his parents to even sign up for this trial, it was literally the first human trial where this has happened. And I do want to ask you, because for the last 2 years, we've also been trying to get Alyssa Tapley. She's the other 13-year-old child with leukemia. And she was cured by CRISPR and gene editing, and she actually wanted to come physically to India. She's now 15 and thriving, but her doctors have not been allowing her to come because her immune system is still pretty susceptible. But it's just amazing, 2 children saved by gene editing. It was terminal cancer with her as well. But here,
yes.
Was it, at which point do parents, tell us about the parents and their psychology in signing up for this human trial. How did you convince them, or did they opt for it? And number two is that, you spoke about that it took 6 months. First, just the detective story of this, that you map 3 billion genes, you find that one mutation, you make a personalized therapy, then that works, and then you drop a soap cell. It's just amazing, but how scalable is this, Kiran? When you were talking about it taking 6 months, what's the cost? Is it scalable? Can the hope of this story transmit to many other millions of parents whose babies are not well?
Yeah,
So
so a couple of
one is the
questions there,
human
too.
trial, and second is the scalability, yeah.
Yeah. And I've had the pleasure of meeting Alyssa Tapley, who you mentioned. And yeah, like last time I met
Sorry,
her, she was
Kiran, we
doing...
can't hear you very well. Will you just speak a bit louder?
Sorry.
Yeah.
Yes, I had the pleasure of meeting Alyssa Tapley last year.
Oh,
And
okay.
she looks great. As you said, put her cancer in remission, a few years back, and she's been doing incredibly well. And our hope is KJ will have, a similarly good outcome. And so, yeah, sorry, what was your first question? I lost track of that.
The first question was that, at which point did the parents decide,
Oh,
was
yes.
there a danger to this, when they signed up their baby for a human trial that's never been tried before? Was there a big fallout that could happen? Help us understand the psychology of what was at stake.
Sure. So I should say first that everything that we did here, I did collaborating with a good colleague, a good friend and colleague of mine at the Children's Hospital of
Rebecca.
Philadelphia, Dr. Rebecca Ahrens-Nicholas. So she deserves as much credit for this as I do, if not more. She's a pediatrician. I'm a cardiologist. I actually take care of adult patients, although I do have expertise in gene editing. She's the one who really was interfacing with the patient and the patient's parents, Kyle and Nicole. And so about 6 weeks after KJ was born and we had figured out what his misspelling was, in the laboratory, we worked really quickly and were able to come up with a solution. So before we had a solution in hand, we didn't want to talk to the parents and offer them any false hope, right? Because if we didn't have a good solution, then none of this was going to happen. Why even bring it up? But once we had a good solution and then we talked to some potential partners to get the drug manufactured, that's the point at which Becca approached the parents and said, we have something new. It's never been done before. We know it's going to sound like science fiction, but there's a possibility that in your child's case, we might be able to correct his misspelling. And she explained it very carefully. I think, I wasn't involved in the conversation, but she spoke to them for a good hour and a half, 2 hours, just explaining it from A to Z. They had a lot of questions. And for something like this, it's not something that you're going to sort out in one conversation. She had many conversations over the next several months about this. And over that time, they learned more and more, and they got to the point where they understood the science as well as any scientist, to be perfectly honest. But in that first meeting, they were fantastic, and they understood that there was a lot of risk, that we might not even be able to make the treatment in time because no one had ever made a drug that quickly from scratch before. But their perspective was, if we could learn enough from trying to do this, even if we couldn't help KJ, if this would be useful for other kids someday, they felt it was important that we try to do it. Which you couldn't ask for, from more from
It's incredible you said that. I haven't met those parents, but baby KJ's parents, but with Alyssa Tapley and her parents, we had this similar conversation about the risk involved in being a first human trial on gene editing, which is like literally changing the spelling of your code, your source code. And it's amazing because Alyssa Tapley, and she was 13 then, and it was really her decision. And she said, even if this doesn't work for me, I want to, I know I'm terminally ill, and I want to be part of something that might move the science for the rest of humanity, So that's an incredible psychology there. And it's amazing that baby KJ's parents had the similar motivation, That's quite brilliant.
Absolutely.
But,
Absolutely. It's equal parts bravery and selflessness, right? They're thinking not just about their own child, but about other children and other parents, which is, very, very commendable.
So, the second part of my question was about the scalability of this, that it's such a hopeful story, but can this transmit for others at population scale?
Yeah, so it comes back to the technology as I explained it. You have this GPS, and you put in the address, so to speak, in the genome, and then it goes to that place and then makes the change. And that programmability is what allows for the scaling, right? So KJ has his own unique misspelling. The drug we made for him isn't going to do anything for anyone else. However, if all you
Sorry,
need to
I didn't
do is,
get that. I'm not sure if the audience
yeah,
did.
sure. It's about the programmability, changing the GPS to a new place in the genome. So in KJ's case, the GPS was set, the address for his specific misspelling, his mutation, right? So that treatment would only work for him. It wouldn't work for anyone else. However, all you need to do is change that GPS. So the next kid that comes along, in principle, you change the GPS to match
My
the
God.
site of their misspelling, their mutation, and now you have a version of the drug, the same drug, just change the GPS, that could potentially help them. And you can do that again and again and again. So in terms of scaling it up, in principle, you could do this over and over and over again and individualize to each patient. It could be a kid with one of these diseases. It doesn't have to be kids. It could be adults with genetic diseases. And in fact, you can extend this even further and say, well, it doesn't have to be rare genetic diseases. You can actually treat much more common diseases like heart disease by using the same strategy. And instead of pointing it to a misspelling that's causing a devastating genetic disorder, it can actually point it at a cholesterol gene and turn it off. And then the idea is in a person who has heart disease, who is at risk for heart disease, you're pointing it at a cholesterol gene, and you're turning that cholesterol gene off. The cholesterol levels in the blood come way down, within a few days. And once they are down, because you're making changes in DNA, they are down for good. They never
My
come
God.
back up again. So you've permanently reduced their cholesterol levels. So in terms of scaling, we do think that we can help a lot of kids like KJ who have genetic diseases of various types caused by all these different misspellings and all these different genes. But we also think that this can be scaled to help people who are at risk for the leading cause of death worldwide, which is heart disease. So I think we all will potentially benefit from this technology. Now, it'll take time. I don't want to I don't want to
Misrepresent, yeah, the hopes, I
misrepresent
think.
exactly what's possible here. Yes, exactly right. It will take time. And for now, this is a very big limitation. For now, those soap bubbles I mentioned, they only really go to the liver, right? So if you have a disease that affects something other than the liver, then we don't yet have a good way to deliver CRISPR into that. So there are a lot of diseases, whether they affect the brain, whether they affect the muscles, whether they affect the heart, which I care about as a cardiologist, whether they affect the kidneys or the lungs. We're not quite yet at the point where we can make these therapies. We're getting there, but it will take some time. But as of right now, if there is something in the liver we can fix, in theory, we now have the ability to do that.
This is the most incredible story, Kiran. Even the vocabulary you're using is, we've been talking about at Synapse about genome mapping and how important it's becoming, in therapeutics alongside gene editing and bioengineering and all of that. But just now, just the word you used, the GPS, the fact that you can have a GPS to go and deliver a drug in some, absolute precise corner of your body. This is just it's mind-blowing stuff, So a big salute to you for the kind of work that you and Rebecca have done. But Kiran, I want to come to before we come to some of the other implications of gene editing, and you've written the CRISPR generation, and I want to share that with the audience. But before that, I do want to share the other marvelous idea you had. You kind of alluded to it, but the concept of having vaccines, genetic vaccines for heart attacks, that's another mind-blowing idea. Do tell us what that really entails, and then how close are you to the fruition of that?
That's actually making very good progress. So as I said, you can point the GPS, you can point CRISPR to wherever you want, right? Any of the 20,000 genes in the genome, any location out of those 3 billion letters in the genome. And so what we started working on almost 15 years, more like 13 years ago now, when CRISPR first came on the scene, was pointing CRISPR to any one of several cholesterol genes. So there are genes in the liver that push cholesterol levels up, and then there are genes in the liver that push cholesterol levels down. And the reason we have both types of genes is to achieve balance. You want not too high, not too low, sort of the Goldilocks, principle. And so you have these, these contrasting effects. Now, it turns out that none of us is really in danger of eating, of not eating enough cholesterol in our diet. So the genes that push up cholesterol levels, we don't really need them. If you get rid of one of them, it's okay. And in fact, about 2
Kiran, I
to
have a question
3%.
to ask you there, which
Yeah,
is even
sure.
before heart attacks. Are you telling us that we can switch off the cholesterol gene, which means you can eat all the carbohydrates you want and nothing will
Well,
happen to you?
hold on, hold on. So, the answer is yes, but also no. So, yes, you could turn off a cholesterol gene well in advance of when you might get a heart attack. I mean, in my mind, the ideal time to take this would be when you're about 20 years of age. You're not at risk of getting a heart attack for the most part until you're, into your 60s or 70s, but it's a chronic disease process. It takes decades to build up, and exposure to cholesterol over the lifetime is what puts you at risk for heart attack, and stroke for that matter as well. So if you can turn off the spigot early, so to speak, and reduce the exposure to cholesterol, yes, you can reduce the cholesterol. Now, does that give you license to, as you said, eat a lot of carbohydrates or eat, bad diet, not exercise, not take care of yourself? The answer is it gives you a little bit of margin, but the truth is that you can undo the good that you do with reducing your cholesterol levels, by not taking good care of yourself, by making poor decisions with respect to health and lifestyle. And then there are other diseases you have to worry about. If you just eat carbohydrates all the time, you're probably
Right.
putting yourself at big risk of getting diabetes. And so it's not just about heart disease, it's about staying healthy,
Right.
in all ways, right?
But
But I do,
ancillary
yeah,
question
yeah.
to that is that if you can switch off a cholesterol gene, as you discover and map the human body to this level of minuscule detail, is it possible that we'll live to see a generation where you can switch off all the kind of diseases which are systemic and you can like just switch off all those levers? And so you really kind of, in one switch, eradicate many of the diseases that haunt the human race right now?
I think it's possible. So we're
Wow.
starting with heart disease. We know that there are cholesterol genes. We know there are people walking around who are naturally born with cholesterol genes turned off through changes, misspellings in the DNA, but good misspellings that they inherited from their parents. They got lucky. They won the genetic lottery, as I like to say, because the genes turned off, from when they're conceived, from the time they're born. They are exposed to low levels of cholesterol for their entire lifetime. And we know that reduces their risk of heart attacks and stroke by 80%, 90% compared to the average person. That means it's pushing off heart attacks decades to the point where they're probably not going to live long enough to even have a heart attack. They're going to, have some other thing, some other issue. And so if we can do that with gene editing, if we can do that with CRISPR and say any 20-year-old and basically turn off the cholesterol gene, just like those people who won the genetic lottery, but now you don't have to win the lottery. We can do it for you, right? Then yes, if you do it early enough, it will push off again heart attack and stroke by decades. You will live longer on average. If enough people in the population took this, it would improve life expectancy because heart disease is the leading cause of death worldwide. It doesn't matter where you are in the world. It doesn't matter if you're in India. It doesn't matter if you're in the United States. It is the leading cause of death worldwide. And so there's the potential to really make an impact on human longevity. But exactly as you said, it's not just heart disease, right? There are many other conditions we'd love to be able to treat, from the get-go. We'd like to be able to tackle cancer. We'd like to be able to tackle diabetes and neurodegenerative diseases and lots of other issues. And I think it'll take some time, but I do think this gene editing strategy, if you find the right genes, find the right levers, as you described it, yes, I think maybe a generation from now, maybe 2 generations from now, we could get to the point where routinely individuals, when they're at a relatively young age, will get a combination gene editing therapy that will pull on this lever, push this lever, and re-engineer health in such a way that people will inevitably live healthier, longer lives. I think
Wow.
that is a
This is pretty sci-fi stuff, it's really amazing, Kiran. So one question that's remained unanswered is that what is the cost of this now and what do you foresee it'll become? Will it be affordable to do this?
Yeah, so at the present time, this is so new, right? And we're just learning how to do this, and we're still iterating and improving the technology, and figuring how to scale it up. So it's relatively expensive, But as I explained in KJ's case, the standard of care is you're in the hospital for a long time. And I didn't really go into it, but you're getting things like dialysis and you're getting some pretty expensive medications to try to keep the ammonia levels under control. And then the only way we really have to definitively treat it, or at least before KJ was treated, was liver transplant. And that's not a cheap, inexpensive procedure. That's a big deal. That's a major surgery, and there are a lot of risks associated with that. And then you have to be on a lifetime of immunosuppression, so that means more chronic medications. And so, to put it in context, in U.S. dollars, a liver transplant, it's about $1 million, right? And that's the standard of care. And to make one of these gene editing therapies right now is several $100,000. So it's already comparable to the standard of care. As we get better and better at doing this, and as we scale it up, and economies of scale will kick in, that cost will fall. It starts at several $100,000, but I think give it a few years and we get it down to tens of thousands of dollars, and then maybe eventually when this is really scaled up, you get it down to thousands of dollars, and then you're really talking about entirely rewriting, human disease for, relatively affordable price, then I think, it makes a lot of sense.
But Kiran, so, now that we've kind of explored the miraculous potential of this, there are all the other ancillary questions. And, you wrote The CRISPR Generation, which was about the Chinese scientist,
He Jiankui.
Is that how you pronounce it? Where he gene edited the germline of twins before they were born. He went to jail for it, and I would love to know your perspective on that in terms of, was he pushing science? Was he taking risks that future generations will thank him for? Because he's kind of really stood by his work. So one, your perspective on him, because you've called it the CRISPR generation. We're being born into, generations being born now, like you said, will be able to switch off, switch on every aspect of their body, and it doesn't only stop at disease. It could go to qualities, it could go to the color of your hair, your eyes, beautification. Jennifer Doudna, when she came up with CRISPR and she won the Nobel for it, she's spoken about having a nightmare actually and seeing Hitler's face and thinking, oh my God, what have I done? What have we unleashed into the world? Because it can have such far-reaching ramifications, So first, do tell us what was your perspective on the Chinese scientists' work, and then I'd like to ask you something more beyond that,
So when the news came out, this was November of 2018. I was one of the most outspoken critics. I spoke up very early and very loudly, and I was pleased to see that the consensus among the scientific community matched mine perfectly. This was bad science. It was a scientific disaster because, frankly, he didn't know what he was doing. And so when he tried to change these embryos, the idea was to make the babies who got the editing as embryos, to make them more resistant to HIV infection. It just went horribly awry. Like, not only did it mess up the gene that he was trying to target, but it also caused a lot of additional changes. It was a scientific disaster. But on top of that...
Just so that the audience knows about that, Kiran, the twins are still alive, and you're saying the genetic experiment went horribly bad. What has happened to the twins? Because there isn't that much coverage on it anymore.
We don't know. We have no idea.
You don't know.
We have no idea if the editing had any negative health consequences. I hope not, but there is a strong possibility that there were unanticipated consequences. We simply don't know. There's no information that's come out about them. And I'm actually okay with that because they were subjected to this horrible experimentation. I don't want them to be poked and prodded and be very public. Enough has been done to them. Let them be. But I think that highlights that it wasn't just a scientific disaster, it was an ethical disaster. It was framed as a clinical trial, but it had none of the actual conditions of a clinical trial where things are thought through in a very ethical way, where there is informed consent, where there's a balancing of benefits and risks. Unequivocally, in that case, the risks far outweighed the benefits. And the other issue that you pointed out is when you do it as an embryo, it potentially not affects the people who arise from the embryos, but all future generations that arise from those people, because you're changing every cell in the body, including the germ cells, that the sperm, the egg, depending on male or female, and it can get passed along. And so to me, that goes beyond the pale, right? Even if it was scientifically perfect, which it was not, and it will be a long time before it ever will be when you're doing things with embryos for a variety of technical reasons we don't need to get into. Even if it was scientifically perfect, it was an egregious ethical lapse on many levels. You could write a whole, in fact, I have taught lectures and, written books, as you said, about like every way that this was a violation of ethical codes that have been intact since World War II. You mentioned Hitler, the Nuremberg war trial, going all the way back to the 1940s.
But Kiran, at Synapse, we've been examining the celebratory potential as well as the ethical, social, moral implications of all technologies, from AI to robotics to bioengineering to longevity and all of that. So here, one was that you said this was just ethically wrong at every level. To do it to an embryo, it has cascade effects across generations. It was wrong, it was badly done, all of that. But even in the genetic engineering therapies that you are developing, or that Jennifer Doudna and so many others have now made possible, and it's almost available across the counter, it or will soon be, then people will be able to play with the genetic codes of, like I said, it could be your hair, your vanity, it could be particular qualities. You want a better sportsman as a kid, you want a more compassionate child. Like as your genetic detective work gets more and more precise, all of these possibilities could open up. So one, what do you think of that? Is it possible to guardrail it? And do you still think that one should go ahead with this, really, really frontier technology? How do you see it playing out?
Well, look, any new technology has the potential to do enormous good, but also for misuse. And that's just as true of gene editing as any other technology we've ever had at our disposal. And so, as a realist, I would say you have to take the good with the bad. You can try to deter bad actors, but it's probably very, very challenging to entirely eliminate bad actors or prevent them from doing things. You put up guardrails, you put in legislation, you put in regulations, you try to control things. There will always be bad actors who will try to get around it, but that's true in every facet of our lives, right? You can legislate all you want against murder. It still happens, but we deter it by applying very, very harsh penalties, and I think that's the kind of thing that is called for here.
We have to transmit this Zoom call to Jan LeCun because, he was talking about building world models of AI, and we were arguing with him because he kept saying, we'll just put laws around these models and they'll behave perfectly. And we kept telling him that, children don't behave, human beings don't behave in terms of what has been laid out as law. So there's always that possibility of disruption. But just last question, Kiran, which is a more medical question, that, other conversations have been about how complex the human body is, how interconnected, it's a network effect. Homeostasis is kept together by so many different variables. So when you play with the genetic switch of any one aspect of the human body, can it have cascade effects in other unanticipated ways? So is there also still a medical anxiety around doing gene editing?
Yeah, that's a very, very astute question. So it really depends what you're doing. So in a case like KJ, he had a misspelling that was causing disease. And so there wasn't really any question that if we could correct the misspelling to the normal spelling that everyone else in the human species has, there really isn't any possibility of unintended consequences because everybody else, literally everybody else in the human species has that correct spelling and is healthy because of it. So in those kinds of situations, you don't have to worry so much. When you're talking about turning off cholesterol genes, there we have evidence that there aren't going to be unintended consequences because, as I said, there are people naturally born with the gene turned off, and there are enough of those people that you can study them and really be able to conclude, okay, if that cholesterol gene is turned off, are there good consequences? Are there bad consequences? The answer is yes. There are good consequences. They are greatly protected against heart disease. And what we have seen by studying, many individuals like this is that there don't seem to be any adverse consequences. There doesn't seem to be any downside in terms of health. And so that gives us a lot of confidence that if we turn that gene off, nature has already done the experiment for us. Where things get trickier is if you start taking on more complex things like intelligence or, personality or things that are very, very complicated. Then you go in and start changing genes, and then it becomes much, much, much messier in terms of trying to predict what the consequences are. And I would be very, very cautious about, trying to do that sort of.
But what about age? That's the one global conversation now is about longevity and reversing age. So would it be possible to, turn off the switches, the epigenetic switches or senescent cells or whatever it is, the combination that creates age? We had a session earlier where we had scientists and entrepreneurs who were talking about age itself as a disease. So would you be comfortable with switching off those things which create age?
I would be comfortable if we actually knew what they were. I'm not convinced we're anywhere near to understanding what they were. I will say this, if you turn off a cholesterol gene, that is the most surefire way to improve longevity, because that will push off heart attack and stroke by decades. And that, again, as I said, is the leading cause of death worldwide. Maybe if enough people get this kind of treatment, it will no longer be the leading cause of death worldwide. And on average, people will live years longer because of that. So that's probably the most straightforward way to actually achieve longevity. You don't need to find anything new. You don't have to talk about epigenetics or this or that. We already know how to do it. Turn off the cholesterol gene, promote cardiovascular health, help people live longer. But I do take your point. There are other levers to pull on. We just, I feel, don't quite understand what those are and what the potential unintended consequences. But that's why we do research. That's what science is about. It's about discovery, and maybe over the coming years, we'll learn enough about some of these levers that, yes, it will make sense to use something like gene editing to pull on those levers and help everyone live longer, healthier lives.
Thank you so much, Kiran. We showed little pictures of baby KJ before you came online. And it was just like, I literally was grinning ear to ear, seeing the little baby toddling back home and then surrounded with all his siblings. You made that possible. So big salute to you and Rebecca. Thank you so much for joining us.
My pleasure.
Thank you.